NEC 310.4 addresses the requirements for parallel conductors. This section of the National Electrical Code focuses on ensuring that when multiple conductors are used to carry the same current, they are installed in a way that minimizes inductive reactance and promotes balanced current sharing. The core requirement NEC 310.4 is that all parallel conductors must be run in the same raceway or cable, or be grouped together. This grouping is essential for minimizing inductive reactance. Inductive reactance is the opposition to the change of current flow in an alternating current circuit caused by the inductance of the conductors. When conductors are separated, the magnetic fields they produce can interact differently, leading to unequal impedance and thus imbalanced current distribution. By grouping the conductors closely together, the magnetic fields tend to cancel each other out, reducing the overall inductive reactance and promoting more even current sharing among the parallel conductors. Grouping can be achieved by installing all parallel conductors in a single conduit, cable tray, or other approved raceway. Alternatively, if separate raceways are used, they should be grouped closely together. This means running the conduits adjacent to each other, securing them together, or otherwise ensuring they are in close proximity. The primary goal is to minimize the distance between the conductors carrying the same phase or neutral current. The code emphasizes the intent of minimizing inductive reactance, and grouping the conductors is the primary method to achieve this. Now, let's address the question of equal length of parallel feeders. While it is generally desirable for parallel conductors to be of equal length, the NEC 310.4 does not explicitly mandate it. The main concern of the code is to minimize inductive reactance through grouping. The inspector's request for a resistance test to verify the conductors are the same length to the inch is not a standard requirement found in NEC 310.4. The intent of the code is met by properly grouping the conduits together. The resistance test is not a typical method for verifying compliance with NEC 310.4. Minor differences in length are generally not a significant concern, especially when the conductors are properly grouped. However, significant length differences can lead to current imbalances, so it is best practice to keep the lengths as similar as possible. There are some additional considerations. Firstly, conductor material. All parallel conductors must be of the same material. This means you cannot mix copper and aluminum conductors in parallel. Secondly, conductor size. Parallel conductors must be size 1/0 or larger. This limitation is in place because smaller conductors have higher impedances and are more susceptible to current imbalances when run in parallel. Thirdly, insulation type. The insulation type of all parallel conductors must be the same. This ensures that the conductors have similar temperature ratings and impedance characteristics. Fourthly, termination. All parallel conductors must be terminated in the same manner. This means using the same type of connectors and ensuring that the connections are properly torqued. Fifthly, ampacity. The ampacity of the parallel conductors must be sufficient to carry the total load current. The ampacity of each conductor is determined based on its size, insulation type, and installation conditions, in accordance with NEC tables such as 310.15b16. Sixthly, overcurrent protection. Each set of parallel conductors must be protected by an overcurrent device sized to protect the conductors in accordance with NEC 240.4. The overcurrent device must be located at the point where the parallel conductors receive their supply. Seventhly, voltage drop. The voltage drop in parallel conductors must be within acceptable limits. Excessive voltage drop can lead to equipment malfunction and reduced efficiency. The NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. Eighthly, harmonic currents. In systems with significant harmonic currents, it is especially important to properly size and install parallel conductors to avoid overheating and other problems. Harmonic currents can cause increased neutral current and can also lead to increased losses in the conductors. Ninthly, dirting factors. When conductors are installed in close proximity to each other, or in environments with high ambient temperatures, dirting factors must be applied to reduce the allowable ampacity of the conductors. These dating factors are specified in NEC Table 310.15b3. Tenthly, documentation. It is important to properly document the installation of parallel conductors, including the conductor size, insulation type, ampacity, and the method of grouping. This documentation can be helpful for future maintenance and troubleshooting. The resistance test is not a standard requirement of NEC 310.4. The NEC focuses primarily on grouping to mitigate inductive reactance. If the conduits are grouped together between the transformer and the main switch, the intent of NEC 310.4 is satisfied. Additional considerations beyond NEC 310.4 might involve ensuring that voltage drop calculations are within acceptable limits, especially over long distances, and accounting for harmonic currents, which can exacerbate current imbalances. It is also good practice to use properly sized and torqued connectors to ensure reliable connections and minimize resistance at termination points. When dealing with electrical inspections and code compliance, it is always a good idea to maintain open communication with the inspector and understand their specific concerns. While the resistance test might not be a standard requirement, there could be specific reasons why the inspector is requesting it. If you are unsure about any aspect of the code or the inspection process, it is best to seek clarification from a qualified electrical engineer or consultant. This proactive approach can help ensure compliance and avoid potential issues down the road. It is also worth noting that the NEC is updated every 3 years, so it is important to stay current with the latest edition of the code. Changes and revisions are made to address new technologies, emerging safety concerns, and to clarify existing requirements. By staying informed and seeking expert guidance when needed, you can ensure that your electrical installations are safe, reliable, and compliant with all applicable codes and standards. For example, let us say that you have a 480 volts, 3-phase system that requires parallel conductors to supply a large motor. The total calculated load is 400 amps. According to NEC Table 310.15b16, a single 500 kc milk copper conductor with a 75 degrees Celsius insulation rating has an ampacity of 380 amps. Since this is not sufficient to carry the 400 amp load, you will need to use parallel conductors. To determine the appropriate size of the parallel conductors, you will need to divide the total load current by the number of conductors per phase. In this case, let's assume you are using 2 conductors per phase. So, 400 amps / 2 conductors equals 200 amps per conductor. Now, you need to select a conductor size that has an ampacity of at least 200 amps. According to NEC Table 310.15b16, a 3/0 AWG copper conductor with a 75 degrees Celsius insulation rating has an ampacity of 200 amps. Therefore, you could use 2 3/0 AWG copper conductors per phase to supply the 400 amp load. Now, you need to ensure that the parallel conductors are installed in accordance with NEC 310.4. This means that the conductors must be of the same material, same size, same insulation type, and terminated in the same manner. They must also be run in the same raceway or cable, or be grouped together. In this example, you could run the 2 3/0 AWG copper conductors per phase in a single conduit, or you could run them in separate conduits that are grouped together. Remember to apply any applicable dating factors for ambient temperature or the number of conductors in the raceway. If the ambient temperature is higher than 30 degrees Celsius, or if there are more than 3 current-carrying conductors in the raceway, you will need to reduce the allowable ampacity of the conductors. The dating factors are specified in NEC Table 310.15b3. Finally, you need to protect the parallel conductors with an overcurrent device size to protect the conductors in accordance with NEC 240.4. In this case, you would need to use a 400 amp overcurrent device to protect the 2 3/0 AWG copper conductors per phase. Always consult the latest edition of the NEC and seek guidance from a qualified electrical engineer or consultant to ensure that your electrical installations are safe, reliable, and compliant with all applicable codes and standards. Additionally, consider the impact of using aluminum conductors. Aluminum conductors have a lower conductivity than copper conductors, so they must be larger in size to carry the same amount of current. This can increase the overall cost of the installation as well as the size of the raceways and enclosures. Aluminum conductors are also more susceptible to corrosion than copper conductors, so they must be properly terminated and protected from moisture. Also, consider the use of cable trays. Cable trays are a popular alternative to conduits for supporting and routing electrical cables. They offer several advantages, including ease of installation, flexibility, and the ability to support a large number of cables. However, cable trays must be properly designed and installed to ensure that they can support the weight of the cables and that the cables are properly secured. The NEC contains specific requirements for the installation of cable trays, including the spacing between supports, the type of fasteners to use, and the grounding requirements. Furthermore, consider surge protection. Surge protection devices (SPD) are used to protect electrical equipment from voltage surges caused by lightning strikes, power outages, and other events. SPD are typically installed at the service entrance of a building, as well as at individual equipment locations. The NEC contains specific requirements for the installation of SPD, including the type of SPD to use, the location of the SPD, and the grounding requirements. Also, consider grounding and bonding. Grounding and bonding are essential for ensuring the safety of electrical systems. Grounding provides a path for fault current to flow back to the source, which helps to trap the overcurrent device and prevent electrical shock. Bonding connects all metal parts of the electrical system together, which helps to equalize the voltage potential and reduce the risk of electrical shock. The NEC contains specific requirements for grounding and bonding, including the size of the grounding and bonding conductors, the type of connections to use, and the location of the grounding electrode. Be sure to use proper lock nuts and bushings. Lock nuts and bushings are used to secure conduits to enclosures and to protect the conductors from abrasion. They must be properly sized and installed to ensure a secure connection and to prevent damage to the conductors. The NEC contains specific requirements for the use of lock nuts and bushings, including the type of lock nut or bushing to use, the size of the lock nut or bushing, and the method of installation. Don't forget about wire markings. All conductors must be clearly marked to indicate their size, insulation type, and voltage rating. The markings must be durable and legible so that they can be easily identified. The NEC contains specific requirements for wire markings, including the type of marking to use, the location of the marking, and the information that must be included in the marking. And consider labeling. All electrical equipment must be properly labeled to indicate its function, voltage rating, and ampacity. The labels must be durable and legible so that they can be easily identified. The NEC contains specific requirements for labeling electrical equipment, including the type of label to use, the location of the label, and the information that must be included in the label. Finally, remember record keeping. Keep accurate records of all electrical work, including the conductor sizes, insulation types, ampacities, overcurrent device ratings, and grounding and bonding connections. These records can be helpful for future maintenance and troubleshooting.